Hello, welcome everyone. We'll discuss what a digital image is today, and we'll learn how to create images in Python and then how to manipulate them to access pixels. A grayscale digital image is a rectangular array of numbers which represent pixels. Each pixel can take an integer value in the range from 0 to 255 inclusive of both these numbers, as these are represented by 8-bit numbers. If the image is a color image, then there would be 3 such arrays. The size of this array is actually the resolution of the image. For example, if we take a modern camera like Nikon D5, the size of the image would be typically 3712 pixels times 5568 pixels. So this would be the resolution of the image. So we take the top left pixel as the 0, 0 pixel as shown in this diagram. So this would be 0, 0. This is the row index, and this J is the column index. So you can see there are 0, 1, 2, 3, 4, 5. That means 6 rows and 8 columns in this image. So therefore we call this image a 6 by 8 image. Now, if we want to access a particular pixel, for example, pixel 2, 3, we would first specify the row index and the column index. Now, if we take a color image, we can consider this as 3 such planes as in the grayscale image, one for blue, one for green, and one for red. So this one is a BGR image. Blue, green, and red color planes are there in this image. So if we access pixel locations such as 2, 3, we will get 3 values, B, G, and R in Python. Each value is in the range 0 to 255 inclusive, and as a result, you can represent different colors amounting to 2 to the power of 8 times 2 to the power of 8 times 2 to the power of 8 many colors. What we want to do now is to create 2 such images in Python and then try to access its pixels. So to do that, we can have this Jupyter Notebook Magic Matplotlib inline to be able to show these images on the Jupyter Notebook itself. And we have to import OpenCV by saying import CV2 as CV. Then we will import NumPy for the array manipulation and creation. And then for plotting, we will import Matplotlib pyplot as PLT. And on this line number 5, we actually do the image creation. So you can see we are creating a 2-dimensional array, im equals np zeros 6, 8, data type np uint8. So you can see the size of the array is 6 by 8, data type is uint8. Uint8 means that these are 8-bit unsigned numbers. So that means each number can represent one of 256 values. So the smallest is 0, and if you have all ones, you would get a 255. So if you go beyond that, this data type does not have the capacity to represent. So then we have im2, 3 equals 255. That means setting the pixel at 2, 3 to value 255. That is the brightest. Then we have the image plotting code, which I will not describe, but this is very important. I think this has a mistake also. When we look at the coding window, you will see what this mistake is. Actually, we have to set the minimum and maximum intensities that we would want to have. Vmin equals 0 and Vmax equals 255. So the reason for this is we have intensities from 0 to 255. We do not want Matplotlib to take the maximum intensity in this array, the current array, and treat it as the highest intensity. We want 255 to be treated as the highest intensity. Okay, now let's go to the coding window and have a look at it. Okay, you can see here we have written Matplotlib inline and then import CV2 as CV and then import NumPy as NP, import Matplotlib pyplot as PLT, and then we are creating the image. Im equals np0 6,8, data type npu int 8, and then we are setting the pixel at 23 to 200, and then we can print that also, that value, and then we are plotting that. So if we execute that, you are going to get this image displayed. Now, for curiosity's sake, let's set this number to a value like 255. What would you see? You should see the maximum brightness in that pixel. Here you can see the maximum brightness. Now, if I increase this to 300, will you see the intensity increasing further? No, because uint 8 cannot represent numbers beyond 255. Then you will see the effect. So I will expect you to explain what this effect is. Another example, if you set this as 256, what will you see? You will see a totally black image. So you can observe the value that it displays also. If you put 256 here, you will get 0. If you put 300, for example, what will you see? So you will see 44 here. So I think you can guess what the reason is. Okay, so we will move on to looking at the color image creation as well. So if you want to create a color image, the code is the same as before, but the difference is instead of having 6,8, 6 is the height, 8 is the width, we will have 3 such color planes with the third index as 3. So when we are setting image to 3, we have to give 3 numbers, because each location, when we address like this, we'll need 3 numbers for the 3 color planes for blue, green and red. But actually, as we are doing this in Matplotlib, this stands for red, this stands for green, this stands for blue. So if you set this as 0 and this as 0 and run this, you should see red. Yes. So then the second number is for green. So we set that to 255, the maximum intensity, and then run this and you see green. And then if you set this to 0 and this one to 255, you will see blue. Okay, so I think now you understand what these numbers, 3 numbers represent. And remember, in here, when we displayed, we had to use the color map gray to interpret these numbers in pixels as grayscale values, considering the minimum number to be 0 and the maximum number to 255. Now let's set this as 1 and run this, and you should expect to see a very dark pixel. You cannot even see that, but if you do not set these two, then Matplotlib will scale it and show that as full bright. We do not want that. That's why we had these two numbers, the minimum value and maximum value, specified by us. Okay, that's about image creation. And then we will look at displaying these opening an image and closing and displaying it with Matplotlib. Okay, so in this image, you can see I am importing CV2 as CV and then import matplotlib.pyplot as plt. I'm reading an image called mr.jpg. This file is in a folder one level above this Jupyter notebook, and inside there is a folder called images, and there I have this image. I can show you that now in this window, in this coding folder. You can see I have the images folder, but I am actually doing the coding in intensity transformations. That's why I moved one folder up and then access the images folder and they access this image. Okay, then I am doing a color conversion. You can see cv.convert color. I'm taking the original image imgo and converting using the enumeration cv.color underscore bgr to rgb. So you can see when OpenCV opens images, they are opened as bgr images. But for Matplotlib to be able to properly display, we must convert them to RGB images. Now IMGC is this color converted image. So you can see I'm creating two axes to plot both these figures, and this is the original image right here, and this is the color converted image right here. Which one has the right colors? So obviously the second one has the right colors, so here the color planes have been switched. That's why you see wrong colors. Okay, now we will see how OpenCV's high GUI can be used to display these images. In that case, you do not have to do any color conversion because the images are opened as BGR images and they are interpreted as BGR images. Okay, in this case, import CV2 as CV, import matplotlib.pyplot as plt, and open the same. I open the same image saying imread color, opening that as a color image. You can open them as grayscale images and so on. And then creating a window in OpenCV, high GUI window, cv.name window, and we identify the window using a string. So here the string is image. Then cv.window auto size. So there are some parameters that you can set. So I'm setting auto size. Then cv.imshow, in that window called image, you set the image to be displayed, and then you have to say cv wait key 0. So it will wait until the keyboard input is given to close the window. You can specify the number of milliseconds also to keep the window open. If you say 500, it will be showing the image for 500 milliseconds. And then you have to say cv destroy all windows. If you run this, so it will display the image right here, and then when you do a press, it will turn that window off. Okay, so I think now you understand how to display an image using OpenCV, which is actually sometimes convenient. Now we can look at how to display the image properties. Here also in this code, I'm opening an image, and I'm opening that image as a color image, and I'm doing the color conversion to be displayed using Matplotlib, and then I'm displaying that image saying ax.imshow img. Then I'm printing img.shape. So I must see the height, the width, and the number of color planes displayed in the shape. And then size would be the multiplication of all bytes. That means the height times width times the depth, or the number of colors. 3 color planes in the image, 3, and then the data type. So you can see the image is displayed. It's a 490 in height, 908 in width image with 3 color planes. It's a color image, and when you multiply these 3 numbers, you would get 1,440,600, and the data type is uint8. Okay, let's get back to the slides. When you already saw how to display the images using Matplotlib, OpenCV. So you're displaying using Matplotlib, we need to do this convert color operation. Otherwise, the images will not look with the right colors. And this is the way of displaying using OpenCV's high GUI. Remember to do destroy all windows. Then display image properties, we looked at that code. Now let's think about increasing the brightness of an image. In order to do that, we can open an image and then we can just add 100. Now, is this correct? Because remember, images are represented using uint8 numbers, and when you add 100, can something wrong happen? So we will look at it when we look at the example. And then the other way of doing that is cv.add img, 100. So this is image B, this is image C. So I am displaying the original image here, then the image with this operation. So I am using that as a title for that so that it's easy for us to see. And then the third one is this brightness increase done using OpenCV. Okay, so what is the reason for img plus 100 operation to be incorrect? The answer is that images are represented using uint8 numbers. Data type is that, so therefore you cannot just add 100 to that. Okay, now let's look at this brightness increase. So we open the image here and we are adding 50, not 100 actually. So then using CV add also and displaying those images. So you can see this is the original image and you can see the artifacts here. And this has the brightness nicely increased by 50. So what is the problem here? You can see the brightest areas in the image, that means the facial pixels. When you add 50, they go beyond 255. So this is the reason for this problem. Okay. Now we can look at how to do this operation in a loop using loops, but actually this is not a piece of code that you should use in practice, because when you access pixels using loops, it's quite slow. So therefore this is just for the purpose of demonstrating that you can access individual pixels. So for this I have written two functions, image brighten 1 and image brighten 2. So let's see the difference later on. So first these two functions take arguments, two arguments. One argument is the image itself and the shift 50 or 100 amount of intensity increase that we want. So from the image I extract the height. Now if you take this image, the height was 490, that number, and then I extract the width W, and then I create an array to hold the results np zeros with the same shape as the image.shape, comma, image.datatype. So it will be a uint8 because the original image is a uint8 image. Then I run my first loop. In the vertically downward direction, I goes from I in range 0 to h, and the second loop is for the horizontal direction, rightwards, j in range 0 to w. Then I have I and j, and I access result I and j, and I set it as image ij plus shift. So you know that this operation is not correct because image ij is a uint8. Then image brighten 2 function is the same two loops, but here rather than just saying image plus 200 the shift, I say minimum of either image ij plus shift or 255. So there you can see if image ij plus shift t goes beyond 255, you would just put 255 into results ij. So therefore what you get from here will be, definitely will be from 0 to 255, not more than 255. So I'm taking the original image, then the image B with image brighten 1 function, which does the wrong operation, image C with image brighten 2 function, and I'm displaying, so we get the same expected results as before. So image brighten 1 is incorrect, image brighten 2 is correct, but the intention of this code is to show that using two loops you can access these pixels. Okay, so in regard to using these loops, do not use this code in practice because they are inefficient, and if possible you can use a Python. I have not been able to successfully use it, but I think you can do that, or you can use OpenCV filters, OpenCV functions. They are fast. So now if you think about a convolution operation, first of all we'll see this now. If you had an image and this image is m comma m and in columns and m rows, how many operations do we have to do if you want to increase the brightness? So it is a big O mn. You see we have to access every pixel, but if you want to do an operation for at every pixel you have to do a convolution operation. That means you have to multiply by a k by k window what is underneath. For example, in this case 3 by 3, what would be the computational complexity? So it would be a big O times big O mn k square. So it is a bit of a complex operation. Okay. Now we can look at how to manipulate these color planes, zeroing them out. Now you can see I'm opening an image. I'm trying to see here in this one more piece of code where I try to see whether the image has been opened. If the image is not found in this location, actually there is a lot of trouble. It's hard to debug also. So it's always good to have this assert. If the image is not there, you would print a message saying image could not be read. So the color conversion has been done here. Now you can see what the operation that I'm doing here. So I will write it in big letters, img, all the rows, all the columns, and color planes 1 to 3 I'm setting as 0. So you see this says all rows and this is all columns, and this one, the third index, can be either 0, 1 or 2 because there are only 3 color planes. So when I say 1 to 3, 1 to 3 actually gives in Python 1 and 2. You know, the last index is not taken. So therefore I am now this stands for red because I have done the color conversion. This is green, this is blue. So when I say 1 and 2, I am actually setting green plane and the blue plane to 0. Then what must you see? You should see the image in its red pixels. So we'll look at this code again. So you can see here is the code, and in this I have the assert operation, and then this operation where I set green and blue planes to 0. So when I display that, I must see a red image. So we can try not see 1 0 to 3, but we can try 0 to 2. That means red and green are set to 0. Then you should see blue here. Run that and you can see blue. So I hope you understand what this means. Okay. So in summary, what we have seen today is that a grayscale digital image is an array of 8-bit unsigned integers in the range 0 to 255 inclusive. We call each such integer a pixel. Color images have 3 such arrays or planes, one for red, one for green, and one for blue. And we saw that when you open images in OpenCV, the representation would be blue, green, red. And if you want to display them using Matplotlib, you should have the color conversion to RGB because that is interpretation there. So we can manipulate an image using OpenCV functions or a pair of loops. A pair of loops is slower, but using OpenCV functions, it would be faster. So you understood what pixels are, the meaning of having uint8 as data type, and how to zero out color planes, and how to access individual pixels. Okay, thank you.